Hello, everyone. Welcome to the sixth and the final workshop that we are putting on that started out over the summer. We've done 5 so far, and we have about 5 hours of content along with that. And we've had several hundred people from all over the world participate. So really thank you, first off, for those who have spent time on these Zoom meetings or following us on YouTube, and all the encouragement that you've given us during and after the sessions along the way. David's sponsor has put in a lot of time crafting some really clean and some really powerful coding examples that have been the foundation for this entire workshop sequence. And he's here again today. How goes it, David?
Great. So this morning, I noticed that USAA, got beat by the Netherlands. So I thought of you.
You call it this morning. I call that an hour ago for me.
Yeah.
Yeah, we actually had my daughter's birthday party, and then we came back and caught the second half of it. And they made it close for a while, but they failed to advance. So
yeah, I had a feeling we would lose because usually the European teams are better most of the time.
I mean, the Dutch system here, and I'm in Amsterdam for those who don't know already. I think there are 18 million total population compared to 400 million in the US. So it's pretty impressive when these smaller nations get together and put up teams that seem to dominate, year in and year out.
Yeah, it is.
Yeah. But I digress from the sports talk, and I'll share it with you as always in the chat, links to some of the older material, just the overview of what each of these workshops has been about, where you can find data and code for all of the examples. And then you're able to access, going back in time on YouTube, all of the other ones that we put together, and you can watch the full session, or you can watch some summary sessions as well. We've covered a lot of material, especially around supervised machine learning during the sequence. We started out with regression analysis, looking to predict numeric outcomes, and then more recently moved into classification models, such as decision trees, that help us make categorical predictions. This will be the end of this 6 workshop cycle, where we focused on Python and Scikit-learn. David and I will be putting on something early next year that we'll be in contact about, where we start looking at AutoML and just some more advanced machine learning models, or at least approaches to starting to do it from a perspective of putting things into production, than some of the more simple examples that we've covered during the sequence. Today, if you've got any questions on the material that we're covering, or what material you'd like to cover next, please let us know in the chat if you're with us on Zoom. And the same goes for YouTube. I see people that are up there adding in information or comments right now, which is great. I will be sort of helping David along with any questions that are coming in, and maybe calling out some clarification points from the material that he's going over. But I think if there are not any more questions to start off right now, David, if you want to just go ahead and share your screen, and we can kick off this 6th workshop.
All right. Thanks, Alex. So today, my goal is really just to put everything together. So we've had 5 sessions. We've covered a lot of material, different modeling types. We also learned about Scikit-learn pipelines that allow us to bundle our feature engineering steps with our models and easily train them. So today we're going to introduce one new model. It's called a random forest, but since we are already familiar with decision trees, it's really just an extension of a decision tree. And then we're going to put together 3 modeling pipelines. We're going to fit a logistic regression model, a decision tree, and then a random forest with our feature engineering steps. And I'm going to show you how to train those efficiently and quickly using something known as Python list comprehension. So this is a way you can quickly iterate through different model combinations with different feature engineering pipelines and just quickly evaluate them and see how they do. All right, so let's go ahead and get started. So as usual, I like to have all of the libraries we're going to use and packages in this setup code chunk here. So here, the important thing is we're going to import 3 different models, the ones we're going to be fitting today. So we have our logistic regression classifier, from the linear model module from Scikit-learn. Then we also have our decision tree and then random forest classifier. And we're going to use the same feature engineering steps that we've developed in prior sessions, just to make things a little bit easier to follow. So this will go ahead and set everything up, load in all of our packages, and we'll be ready to go. Now, again, this is just a quick review. We went over this the last 2 sessions, but I did want to show you what the data set looks like. We'll still be working with the leads DF, and this is a marketing data set that tracks people coming to a website, and the source of these people, whether it was email or they found the website through maybe a Google search, and then attributes about these customers. So how long they're spending time on the site and whether they purchased a product or not. So product purchase in this data set is our outcome variable. So this has our labels, and we're trying to predict the yes or no in our classification model. So we really want to be able to score new leads that come into our website and give them an estimated probability that they're going to make a product purchase. And then based off of that, we can go ahead and try different marketing tactics, whether if someone's highly likely to buy a product, we would probably do something different versus someone who is not very likely to buy a product. And as a reminder, let's say that we've spoken to the business stakeholders here, and they told us that, for this to be a usable model, for it to be useful for them, we have to correctly identify customers who will make a purchase at least 70% of the time. So the difficulty usually in data science is translating things like this into performance metrics in classification modeling. So here, this would be translated to the recall metric. So if you remember that little acronym that I like to use for remembering what precision and recall are. So precision is another metric, and it starts with a P. So that is your accuracy among your predicted classes. And then recall is your accuracy among the real instances of those events, right? So here we're dealing with recall because here we need to correctly identify the customers who will make a purchase. So these are the real yeses in our data set, the people who really did. So that is our success criteria that we'll be using to benchmark each one of these models against each other to make a final decision in the end. All right, so we have to prepare our data for modeling. So these are the same steps that we went through last session as well, but I'll just quickly review what we're doing. So the general methodology is we have to split our data set into training and test sets, and we're going to fit our models on the training data and then evaluate their performance on the test data, which we have held out of the process this whole time. So to do that, there's a helper function in Scikit-learn, train test split, that will go ahead and create all of these data sets for us. The first argument is your features. So here I take my data frame and I drop the column product purchase, and those are just all my predictors, my features. And then the second argument is your target. So these are known as the label columns or the outcome columns. This is the one that has the yes, no outcome, product purchase. All right, so this is going to give us back our training and test data set. I always like to check the dimensions and have a quick look just to make sure everything is correct. So you can here use the shape attribute of the XTrain data frame, and it tells us it has 996 rows and 6 columns. And here's a quick preview of this. So you can see it's a complete random sample from our data. We can see that the first row in this data frame has an index of 429. So that means it was randomly selected, and it was the 429th row from our original data that got into this training data set. Now, the next thing we have to do is transform this data. We have to build a feature engineering pipeline to get it ready for modeling. So we have to get rid of things like the skewness that we see in all of our numeric columns, and we have to transform our categorical data, such as lead source and then US region, into numeric data somehow. So we're going to be using those dummy variable encodings to do that. So like I mentioned last time, this is always it's not a necessary step, but this is one I always like to take. I create lists of my numeric and then also my categorical features. So we need the names of those columns based on type, just to make it easier for our pipelines coming up. So here, the way it's pretty easy to create them, you just take your training data and then you use the select B types, method from pandas, and you select it by the data type, and then you turn it into a list. So I did that for both numeric and categorical. Right, so everything looks good. We have our 2 categorical features and our 4 numeric features. So now we can go ahead and create our feature engineering steps that we would like to take. So we'll be using the same ones we did last time. And for those, we have certain numeric transformations that we took. So we're going to be doing the Yeo-Johnson transformation. So this is from the feature engine package. So it's a helper package that can do some really advanced feature engineering operations. And this one specifically, what it does is it gets rid of all the skewness in our numeric data. So it's a very good transformation method to get rid of that skewness. And then we're also going to scale our data using the standard scaler from Scikit-learn. And then we're going to use the drop correlated features with a threshold of 0.75. So I just wanted to mention this particular numeric transformation pipeline because it's going to come up in a little bit. We're going to be using this for tuning our pipeline in a little bit. So just wanted to call out that we named this step, right, of this pipeline, numeric transformations. And then we have a step within this pipeline that we labeled remove core. And then within there, we have this parameter, this threshold that we set equal to 0.75. So we're going to have to go into this pipeline in a little bit to be able to try different values of this threshold, right? And I'll show you how to do that in a little bit.
Hey, David, we have one question about why these transformers were selected. And for that, I'll just point people back to the second workshop that we did in this series when we started the regression analysis, and we looked all about how to transform and maximize and improve on your models. So if you go to the second workshop video, you'll be able to see how we talked about each one of these and how it applied specifically to numeric variables.
Yes, yeah. So we did the exploratory data analysis on this particular data set, I think a couple sessions back, and we found that there were 2 columns that were very highly correlated. I think they have a correlation of 0.96. And so generally that is going to cause some problems for a lot of different model types. So logistic regression doesn't do very well with highly correlated predictors. And so generally you want to remove that correlation before you go ahead and start doing your machine learning model. So this was chosen because it's a common, step that a lot of people would like to take because they want to get rid of the correlation, but it's not the only thing you can do. So I did want to mention that there are other methods to remove correlation from your data set. So you can do a transformation of all of your numeric features. You can do something that's called principal components analysis. So I can just transform my data and get 4 new columns. They're called principal components, where it's going to be uncorrelated, right? So all those 4 columns are not going to be correlated with each other, and they're going to capture the same amount of variability that I have in my original columns. They've just been transformed in a linear way to remove the correlation. So that's another possibility that you can do. So I did want to mention that this isn't the only thing you would want to do, right? There's other things you could experiment with. But knowing how to do this, how to set up the pipelines and how to test them and train them really gives you the skills to be able to think of different ways to do it and quickly iterate and try things for yourself, right? So that's the important part that I want people to take away from today. So here we have these numeric transformations. So this is a pipeline object that's got those 3 steps. And then for my categorical transformations, I'm creating dummy variables. So I'm going to give this a label of dummy variables, and I'm going to use the one-hot encoder. So that creates a sequence of variables that are 0 or 1, and they're 1 that indicates that that value was present in the original column, that category. So that's really just one way to transform some text data that you may have into a sequence of numeric 0, 1 indicator columns. And so that's very useful for machine learning. But again, a really good question that just came in is that this isn't the only way to encode categorical values. There are many, many other methods. So I urge you to, a good place to look would be the feature engine documentation. So that package has many more methods for encoding categorical variables, and those might work better for your particular use case. And then the last step is we're going to use the column transformer to just put everything together. So we have certain things we're doing for our numeric data. We have another thing we're doing for our categorical data. So now we need to put it all together into a single pipeline that we can train and have everything be carried out in one iteration, basically. So I'm calling this leads feature engineering. And then for this, we have to use our column transformer. So this allows us to put together different pipelines by applying it to the columns that we specify. So this takes a tuple of 3 elements for each step. So here is numeric features, and then I have my numeric transformations pipeline. And then I'm saying apply this to my numeric features. So that is my list with my numeric column names. So I'm instructing the column transformer to go ahead and carry out that pipeline to a specific subset of my data set. And the same pattern happens for our categorical features here. So here I'm giving this a label of categorical features. I'm taking these transformations, right? This pipeline that we just created above, and I'm going to apply it to my categorical features. So that's the list of my 2 categorical columns, right? Lead source and then US region IP. All right, so now we have put everything together into a single pipeline. And now we have our feature engineering steps ready to go. But as they are right now, we can't really use them because it's just a set of instructions. So to be able to use these pipelines, we first have to train them. And so we have to use the fit method that comes along with these pipelines, and that's what we do next here. So here I have leads, feature engineering, and I'm calling the fit method, and I'm passing in my training data. So it's going to take my training data, and it's going to go ahead and execute all of these steps. And so there is some learning going on behind, the curtain here, is that it's learning how to transform using the Yeo-Johnson transformer, using the data that's present in my training data, right? So it has to determine what's the amount of skewness in my data, what's the best way to transform that to make it a bit more like a normal distribution. It's also calculating the correlations between the columns in my training data, and it's using that to determine if any, column should be dropped or not. And so that's where the term, sometimes people get confused about that. When we fit a feature engineering pipeline, people will say that it's being trained, but that's very different from a machine learning algorithm that is being trained, right? So those are not the same things. Here, it really just corresponds to learning all the different transformations that have to happen with the data that we provided. And of course, the important thing here to remember is you have to use your training data set, not your test data set, and not your full data set, right? So that would be a mistake. So that's known as feature leakage if you use the whole entire training data here. So it's important to learn your engineering steps only on the training data and then leave that test data set completely untouched so that it's an unbiased way to evaluate the model performance at the end, right? So that's really important to do. So this is all we have to do, is pass our trained data to fit. So now it's trained. So now we're ready to use it. We can use the transform method of our leads feature engineering to go ahead and use this pipeline, give it new data, and it's going to go ahead and give us the transform data that it learned from the training data. And the nice thing in Deep Note is it gives you a nice visual summary about all the steps that it went through and it learned, and in which sequence, if you want to explore this, right? These are things you can click, and you can see the exact transformers that are being trained during this whole entire step. So I always like to test my feature engineering pipelines. I think it's important to have a look and make sure everything is working properly. And so I like to make just a quick data frame and see how it does on my test data. All right, so here into my pd.data frame, I'm adding the data argument as leads feature engineering dot transform. So now I'm calling the transform method and I'm passing in x test. That's my test data. So it's going to go ahead and apply those transformations that it learned on our training data, and it's going to transform our test data. And it's going to return a NumPy array. And then the columns is we can go ahead and extract the column names from our trained pipeline with this method get feature names out. So that's going to give us the names in the final NumPy array that's returned to us. So we can provide these to the pandas data frame function here, and we can see how the transformations look, in the end, make sure that everything is looking okay. And you can see we don't have skewness anymore in our numeric columns. Notice that we have 3 numeric columns now, not 4, because one of them was dropped because they were highly correlated. And then we have our indicator variables for those 2 categorical columns, right? So everything is good. So we have our feature engineering steps down, they're trained, and they're ready to be used. So now I wanted to introduce the third classification model type. So in the last session, we talked about decision trees. So I wanted to show you, just to remind everybody what those look like, what type of decision boundaries those make in your feature space. So from our data, our leads DF, we have 2 columns in there, total website visits, and I think another one was tracking the total time on the website. And then we have the label, whether the customer actually purchased our product or not. So this is our yes and no. So you can see the raw data is in the scatter plot, right? So there we have actual customers who either did or did not make a purchase. And then the decision tree model, you can think of it as almost a nested if-else statements. But what this does is it creates these rectangular regions in our feature space where it predicts either yes or no. So it learns how to make these rectangles to cut up our features and to effectively make good predictions in those regions. So you can see in this top left box here where my decision tree model is going to predict yes for everything in that whole entire box. But that's a good thing because most customers there actually did purchase a product, right? We had 2 that didn't, but that's a relatively small error rate, right? So this is how our decision tree found a way to cut up our feature space here. So that's what a single decision tree will do. Now, a random forest is just an extension of these decision trees. All you're doing with a random forest is you're fitting hundreds or even thousands of decision trees, and then you're averaging their results. So it allows you to go away from these rectangles or boxes. When you average thousands of these decision trees, you see that your decision boundaries can become more nonlinear and flexible. So you could have things that look sort of like boxes, but they could also be ovals and things like that because you're averaging thousands of these decision trees together. So it can be a pretty powerful technique to improve your prediction accuracy. And I just wanted to briefly mention how this is done, because we have to remember we only have one training data set. So a common source of confusion usually for students is, well, how do I train thousands of decision trees on my one training data set? How I can't do that, right? I have one data set. So how does that happen? So we have to use a technique. It's called bagging, but that stands for bootstrap aggregation. And the secret to this is repeated sampling with replacement of our training data. So this is what allows us to take our single training data set and create thousands of them, from the same exact data set. And the way this happens is we can look at this visual here, right? So on the left side, we have our original training data. So here we have, let's say we have 5 rows. Each one has its own color. And then I have my bootstrap samples from this on the right. And you can see that my first sample, again, I have 5 rows in that one as well, but I got 2 copies of row 1, got 1 copy of row 2, and then I got 2 copies of row 4. So that's what I mean by repeated sampling with replacement, right? You can take a random row from your training data set, and then you can take it again at another step, right? So you're just completely randomly sampling with replacement. So what this does is it creates, we can use it to create hundreds or thousands of bootstrapped data sets. And this is where you are fitting your decision trees to each one of those bootstrap samples. And then you are averaging the results in the end to get your random forest. Now, the nice thing about this methodology, this bootstrap sampling, is that it can really help when you have issues with things like outliers in your data. So if you have a lot of outliers, that could potentially, drastically change the decision boundaries that your models decide to, pick as the best ones. So if you only have a single training data set and lots of these outliers, that could be a problem, right? Your model could be very kind of, it's known as high variance in that case. So those outliers really influence the decision boundaries that you get. But with this methodology here, those outliers are going to be spread out, kind of at random and evenly throughout all of your bootstrap samples. So they will be present in some of those, and they will not be in others, right? And when you average it all together, the effect of those outliers is minimized. So it really lowers your kind of variance due to just these few points that might be influencing your model more than they should be. So that's just the high level kind of intuition behind bagging and why it might be good, right? Why you might think about trying to use this to improve your model performance. All right. And this last section is where we're going to go ahead and take these models and put them together with our feature engineering step and create workflows. So I want to test 3 of these modeling workflows. So I mentioned at the start of our webinar that I want to test logistic regression, a decision tree, and then a random forest. So the way we can do this is we can create yet another pipeline where we can bundle these together. So the first one I'm calling logistic workflow. So here I'm creating a pipeline object, and I'm saying my first step is going to be my feature engineering. And for that, go ahead and run my leads feature engineering that we defined before. So those are all of our transformations for our data. And then for the last step, go ahead and perform a logistic regression. So this is where I instantiate an empty, logistic regression class from Scikit-learn. So it will go ahead and set up the model, and it's ready for training. All right, so this is our pipeline. And then for the decision tree, it's pretty much the same thing. Our first step will be the same. We still have to engineer our data, but the last step is now I'm fitting a decision tree classifier instead of my logistic regression. And for the last one, I'm adding a random forest classifier as my last step. All right, so now I have my 3 modeling pipelines that I'd like to go ahead and tune and evaluate and see how they do. So let's go ahead and execute that. Now we have our pipeline objects. And just as a reminder for how these pipelines are tuned, so the general methodology for this is hyperparameter tuning, where we have already taken our original data and we have created a training and test data set, right? We have our X-train, X-test. But now what hyperparameter tuning does is it will go ahead and sample from our training data, and it will create cross-validation folds, right? So typically you create 5 folds, maybe 10, or you can do 3. So it really depends on your particular problem. But these are, again, randomly sampled data sets from the training data. And then you can go ahead and fit your model on one of the folds. Actually, no, you leave one fold out of the process. So let's say we had 5 folds, right? So you train your model on 4 of them, and then you could go ahead and use that model to make predictions on the one you left out. And then you iterate through until you get through all the folds. So it allows you to fit multiple models. It allows you to estimate model performance multiple times, which is a good thing. You want as many estimates as you possibly can so that you can compare things.
David, when you say 3, 5, or 10, and you say it depends on the particular case, is that because it is your tolerance for computing expense or how difficult it is to make it? Or is it just because different cases are going to lead to a different number that are more optimal?
Yeah, so it really has to do with, again, your computing power, the memory you have available, and that is a function of the size of your data set. So anytime you add an extra fold, you have to remember that you're fitting that many more models, right? So the difference between doing 10-fold and 100-fold is you're going to be fitting 10 times the number of models during your training. So if your data set is millions of rows, that could be the difference between it taking 2 hours and then it taking 2 days to finish, right? So those are the type of things that we have to consider when we choose those type of things. Yep, so it's usually just kind of computing power. And of course, the more, the better, right? Ideally, you would want to do thousands of folds for cross-validation, because that's going to give you a really good idea of how well your model is performing, because you're going to have 1,000 different estimates of the model performance versus just 3 or 5, right? So the more samples you can get, the better. I mean, from a point of view of statistics, because then you could be more confident about the performance of that model. But yes, it's computing, it's your data set size, and it's also budget. All these things, if you're running these in the cloud, they do cost money to train models, and they usually charge by second of training time. So these are all things you have to consider when deciding these things. And so we will be using cross-validation, but we need to set up tuning grids. So these are things that we would like to try to see. So these are parameters of our models that we need to go ahead and test out and see which ones perform better than the other. And we went through this during our last class, but here's again the screenshot from our Scikit-learn documentation. We see our decision tree classifier here. And those are all of the options that you can go ahead and input into this decision tree classifier. So we have our criterion, so we can have the Gini or the entropy or the log loss, and max depth and min sample split. So these are all these hyperparameters that are used to specify this particular model. But again, we don't know which one's going to work the best. So we really have to have a way to test out multiple combinations of this to see which one happens to work better with our data set. So unfortunately, there's no way to know ahead of time what's going to work the best in terms of your hyperparameters, because it's really dependent on the patterns in your data. And so without that, I wish there was a formula or a closed form solution where you would know exactly which decision tree would work the best for your data, but unfortunately, that's not possible. So we have to set up grids to go ahead and test values. So I've done that here. So these are just Python dictionaries. And what they contain is they contain the step name and parameter, and you separate them with 2 underscores. And then the key to this is either a list or it could be a single number, but these are the combinations you want to test for that particular parameter. So let me go ahead and walk through this first example here. So here I'm calling this logistic param grid. So this is my tuning grid for my logistic workflow. So in logistic regression, I have 2 of these hyperparameters. There's a penalty, and then there's this capital C. So that is used to control what's known as the regularization strength, of the logistic regression model. So we don't have too much time to get into exactly what that is, but the default is set to 1 in Scikit-learn, but we want to test different values in addition to that. So you can see here how I have stepped in to this step here. So I first will go ahead and say that this is my logistic regression step, and then double underscore C. All right, so that's the parameter. So it's always your step name that you label in your workflow. And then we have our actual parameter name, which is C. And then you usually pass a list of the values that you would like to test. And also, this is where I mentioned before, having a look at our feature engineering steps. Remember those removing the correlated predictors? So here is an example of how you can do a multi-step and go ahead and tune your feature engineering pipeline as well. So here I am saying feature engineering. And then within my feature engineering pipeline, I had my numeric features, right? That's the pipeline that's going to transform my numeric features. That's what I named it. And then within that, I had a step, and it was called remove core. And then within that, I have a parameter. It's known as threshold in my drop correlated features function there. And so here I'm testing whether I drop it at 0.7 or I drop it at 0.8 here. So I really wanted to show everybody how you can do this, because in the documentation in Scikit-learn, it's not really clear how this is done because they don't have that many examples of it. But if we go back, just wanted to show you to our logistic workflow here, this is what we're going to be tuning, right? So my first step, you can see right here, is my feature engineering. So I called it feature engineering. So that's the label I gave it. And that corresponds to what I'm saying right here, feature engineering. And then you have to ask yourself, so what's in that feature engineering step? So that is my leads feature engineering pipeline. So then we have to go back, right? So you can see this nested layering of steps we've put together. So we have our leads feature engineering pipeline here. And in that, the first step is numeric features, right? And then that has this pipeline, numeric transformations, which is the pipeline above it. And that one in turn has the remove core, and that has the threshold parameter. All right, so this is how you can go ahead and go into any parts of your pipeline. The only tricky part is you have to remember, what did I name them? And what are those pipelines composed of, right? It's a feature engineering step, it's a modeling step, and they could each have sub-steps. So that's how you have to be able to navigate within each pipeline to go ahead and tune them. So that's how I got this option here. And this one I use for all of my parameter grids, just because I want to try it with all the different models. But this is how you would do it, right? You just have to kind of make your way down into your nested, data structures, and then finally get to the parameter. The important thing is that you always end with what that parameter is that you want to test and give the values as the key that you would like to be tested. All right, so I've done that for all of our models here. So logistic parameter grid, also did it for the decision tree. So here I am going to be tuning the criterion, the CCP alpha, and the min sample split. So these were the ones we focused on last class. So I went ahead and just reused those same ones. But here I'm testing whether it's going to be Gini or entropy and so forth, right? Testing different values for my decision tree. And then for the random forest, the only difference really is the random forest has a lot of the same hyperparameters, because remember, it's just fitting hundreds of decision trees. So I'm still going to be testing those combinations I was testing before with my decision tree. But now we also have this hyperparameter n estimators in my random forest here. And so here I'm going to fit 100 decision trees. And then I also want to test, what if I fit more than that? What if I fit 200 decision trees to average them together? So that's what that n estimators stands for. All right, so now I have my grids. And this is, I think, as complicated as it gets in practice, because here we're not only tuning our model hyperparameters, we're also tuning our feature engineering hyperparameters, right? You can do all of it in one step, which is nice, with these pipelines. All right, so here are our grids, which are just these dictionaries that are instructing, what we're going to tune and what those test values are going to be. Now, the next thing we need to do is bundle things together just to make it easier to test and in one line, instead of having to write either a for loop or just multiple code chunks where we're repeating the same thing over and over again. So what I've done here is I've created two lists. So the first one I called workflows. And here I pass my logistic, decision tree, random forest, workflow, pipeline objects. And then I collect my associated tuning grids as well for each one of those models, right? So these are the ones we just created up here. Right, so I have my workflows and my tuning grids in these two lists. And I'm going to put them together into this object here, tuning workflows. And for those of you familiar with Python programming, this is a very common function that we use a lot, zip. And what this does is it puts things together for us, right? It sticks them together in the same order. So when I do zip workflows and then tuning grids, this is going to create an iterable. So this is something that we can iterate through, and it's going to create tuples for us for each element. So the first element of this zip object will be a tuple that puts together my logistic workflow and my logistic param grid objects. It's going to stick them together into a tuple with element 2, right? And then it goes to the next combination. Then it's going to put together my DT workflow and then my DT parameter grid into the second tuple. And then the third one is going to be my random forest. So it bundles things up for us into these 3 tuples where I have my workflow and then my grid for each model type. And then we're going to be able to just iterate through those tuples and train our models very easily. So I wanted to show you this more complicated way of doing things, but this will really save you a lot of time if you're not trying 3 models, but if you're trying 10 different models or 15 different models. You would not want to write, the same code 15 times to train all these models together, because that could really introduce a lot of bugs and errors into your code potentially. So it's best to do things this way, to package things up and have it run. So here we have our tuning workflows. So everything's put together. We have these tuples, 3 tuples in that with our workflows and grids. And now is where I'm going to use what's known as a list comprehension in Python to go ahead and set up my cross-validation grids here. I think it might be helpful if I just show you an example of what this does. Let's say I wanted to square. All right, let me just go ahead and execute that. Oh, sorry. I squared for I in, let's say, range. And so with this simple example, I think it's going to be easier to see, what's going on with these list comprehensions. So this is Python's way of writing a for loop without really having to write a for loop. And it's also usually much more efficient. You can compute things faster this way. And so here, the first argument to these list comprehensions is an expression. So here, notice I put I, and then the 2 stars, that means exponentiation. So I want to calculate I squared for some variable I. And then the next set of input is you have to tell it, well, for what values of I do you want to do this for? So here I'm saying for I in, and then I'm calling range 5. So what the range function does is it creates a sequence going from 0 to 4 for me. So what this will do is it will iterate for each one of those elements in range. So start with 0, 1, 2, 3, and 4. And it's going to return back the squared numbers from that. So this is a nice, clean way, to write these for loops, and it's usually pretty readable. Most people, can understand what's going on here, right? So here we get back this list, and we have 0, 1, and then 2 squared, 3 squared, and 4 squared. So it went ahead and looped through all of my elements in this range 5 and gave me back the squared. So the important thing is you have to line up what this I here in this expression has to match what it's named here for I in range 5, right? That's the important thing. All right, so that's a quick intro to list comprehensions. And this is what we're using here to set up our grid search objects. So here I'm calling this tuning objects. And if you remember from the last time we met, we had this grid search CV. And what that takes is it will go ahead and take your workflow, which is your pipeline, as the first argument. And then it takes a grid as the second argument. And then you specify how many folds do you want, for your cross-validation. So here I'm specifying 3. But here I'm able to do all 3 of my workflows all at once because I'm using this list comprehension methodology. So notice here I'm saying for tup, so that stands for tuple, in my tuning workflows. And that is what we just created here. So here we have our 3, tuples that have our workflow and grid. So the workflow is the first element, and the grid is the second element of that tuple. So I can go ahead and just specify tup0 and tup1. So that's taking the first element and the second, it's extracting it from that tuple. So what it will do is it will cycle through all the tuples that are in tuning workflows, and it's going to set up our grid search CV, all for us in just this one line of code here. So we're going to get back a list that has our grid search objects ready to go. Now we have to train these grid search objects. So we've set them up. We've given them our pipelines and our tuning grid, but now we actually need to call the fit method on them to actually perform the training. And again, this is something we can use a list comprehension for, to just do it all in one line. So regardless of having 3 models or 10 or even 100 models, this one line will still do the same thing, which is why it's so powerful. So here, what I'm doing, now I'm iterating over, I'm calling this tune object in tuning objects, right? So now I'm looking in all of the things that I set up here in this list, above. And then for all of those tune objects, I want to call the fit method on them and pass my training data and then my training labels. So it's going to train every single one of those pipelines for me with just this one line of code. And I'm going to get back a list with my trained pipelines. So it's going to be a list with 3 things, right? So the first one is going to be my logistic decision tree and then my random forest. So let's go ahead and execute this. And this one's going to take a little bit, so if anyone has any questions, this would be a good time. I wanted to, just point out that, we have really fast computers and our data set here is not that large, but even with this is going to take, quite a bit of time. It's going to take about 3 minutes, maybe two or 3 minutes. And this is because, just remember, we're fitting thousands of models all in this one line because we're trying all those different combinations of parameters. We're doing cross-validation, right? So we're doing it 3 times for each combination. And then some of our submodels, like the random forest, we're fitting 100 decision trees for one combination, and we're fitting 200 decision trees for the other, right? So this really quickly adds up. It grows kind of exponentially if you're not careful, right, with your tuning grids, and you can just be sitting here and 2 hours goes by and it's still, trying out all those combinations.
Hey, David, do you know what the specs are for this cloud server?
Yeah, so I think the one we're using right now has 8 gigabytes, for our RAM. So it's not a huge, powerful machine, but it's not bad.
Yep, and now it's done.
Yeah, and our training data was teeny in this case. I think we only had, like 1,500 rows in our training data. So I was expecting this to be done in seconds, but it took a couple minutes. So, all right, so they're done. Everything is done. So with this list comprehension, we've been able to train all of our grid search CV objects, and now they're ready to be used, right? So we can go ahead and take a look to see what's inside these. So here I'm accessing the first element of this trained tuning object. So this would be the logistic regression results, right? The workflow. And I'm accessing the CV results attribute and the params. And then I'm also accessing the mean test score, right? So let's have a look at what we get here. So this is, again, our first, trained object that we have. And you can see that these are all the combinations of parameters that were tested. So the very first one was 0.7 for the threshold of the correlation. We have 1 for our C and L2 for penalty. And then we got a corresponding accuracy for that combination in our logistic regression. So it's 81% accurate for this one. And so this just keeps track of all of our hyperparameter combinations and their associated accuracy by default. But again, that's a little bit of an eyesore. It's difficult to really make sense of that, especially if you have thousands of models. So it's best to put things into a data frame to be able to do some analysis on it. So just like last time, we're using the concat function from pandas, and we're making data frames of these 2 things. So here I'm going to take from the first element of our tuning objects, which is our logistic regression. We're going to take all of those parameters, and then we're also going to take the mean test score and turn those into data frames and combine them column-wise. And this one will be a lot easier to see what's going on here. Right, so for the first row, we get the same result. 0.7 for our threshold, 1 for C, L2 for our penalty, and this was the accuracy that we got. Right, so here you can easily explore all the things that we got. All right, and then if you remember from last time, the attributes best params and best score, that gives you the winning combination for each one. So for our logistic, these were the ones. We could also look for the best combination for the second element of our tuning params, which would be our decision tree. All right, so this was our winning combination there. And we got 0.8 basically, accuracy. All right, so they're all stored in there. And the last thing I wanted to show you is you have to have a way to look at the performance of all of these models and their associated workflows and see which ones work the best. So here is where we can just write a quick for loop. So this is where I enter my models. So these are just the labels I want to print out. So logistic regression decision tree, and then random forest. And then I'm going to loop over. So for I in range, length, of those models. So it's going to be 0, 1, 2. I want to print out what that model name is, and then go ahead and run a classification report on the test data. So notice what I've done here. So for Y true, I give it the test data set labels. And then for my Y predictions, I'm taking my tuned objects that I've trained. I'm indexing them by what the model is. And I'm saying make predictions using that pipeline that you trained on the test data set, on my features. So this will give me the detailed performance of all of my models in one, call. And so I'm just kind of getting everyone ready for our next, session. We've basically done a version of auto ML here, right? This is how most of these auto ML platforms work. It's really about automating how you look for hyperparameters and writing these loops to try maybe 10, 20 models at the same time, and then compare their results at the end. Really, that's really all that this auto ML stuff is doing, right? And we've done it here manually ourselves. And so we can see here, who's our winner. And it seems like there's a tie between all of them. No, a decision tree is our winner. So we have to look at the recall for everything. So we can see our yes class and our logistic regression had a recall of 0.77. So among the people that really did purchase a product, logistic regression was able to predict 77% of those correctly among the real yeses, right? The decision tree was able to do that 84% of the time. And then our random forest was able to do that 81% of the time. So here, our decision tree had the best performance, right? So this could be one way to choose, all right, well, I'm going to go with my decision tree because it gave me the best performance. All right, so hopefully, I know that was a lot to take in, especially with the list comprehensions and all that stuff. But if you go over the material from our last session where we did this for a single model, the decision tree, those are all the steps laid out for how you would do it for one. And then to take you from that to, a pro here where you can do it for thousands of models if you want, all you need is to just take that one little extra step of combining, multiple pipelines and workflows together, and then using those in list comprehensions to just cycle through them automatically with one line of code. And so that's the key here. So if you can do this, you can pretty much build your own auto ML package if you really want. This is the basics of what's going on behind the scenes. And so if you know how to do this, then you really have a good understanding of Scikit-learn and all the possible things you can do with it. And so that was our goal, Alex and I. We really wanted to, in this series, we were thinking about this end product here. If we wanted to really make somebody an expert in Scikit-learn to be able to do all of these advanced things, what would they need to do? And this is the notebook that I thought of in the end, being able to fit multiple models, multiple pipelines all at once, and just comparing their performance.
Yeah, David, you did a fantastic job putting together clear and concise code for this. And you almost set the stage for the inevitability of AutoML. Like you could see yourself going through this and doing it manually at first, putting together, and then starting to go through and do a lot of that, the material you covered tonight. There's going to be a package that is going to help data scientists and others save time when putting together these types of predictions. So my last question for you tonight, and really for the end of this first sequence, is, as someone who's been a practicing data scientist in a variety of companies now for nearly 10 years, I would say, what do you think data science is going to look, or how do you think data science is going to look differently 5 years from now, 10 years from now, and what is the role of the data scientist going to look like?
Yeah, so what I've noticed is we have a lot of tools that have been created, right? So packages like AutoML and visualization tools that are helping data scientists become much more productive and much faster at just delivering results. So that's great. And that's only going to continue. That's going to just speed up. Our tool set is going to become much better over time. So data scientists, I think in the future, are going to be focused, since we don't have to spend as much time, writing for loops like we used to have to tune our models and things like that. I see us spending a lot more time with people in the business. So that's the important thing that data scientists do. So we have a technical background, we're coders, we're mathematicians, and you also have to have that business knowledge. That's a very important part of data science. So the more productive we get with our tools, the more important it is for us to be able to understand our business and deliver results that are going to make a big difference in revenue and just generally in the business, right? We're going to be focusing a bit more on that over time. And what I've noticed, at least in my career, is it used to be difficult to fit even the simplest machine learning models before. So fitting a logistic regression at one point, when R and Python weren't around and didn't really have those modules, you had to do it by hand. So you had to know them, all the mathematics, you had to set everything up yourself. So that just takes a really long time. And so you would spend a month maybe trying to implement that. But that's not the case anymore. So all of this has been kind of automated. And now data scientists are spending much more time on the more complex problems and things like reinforcement learning, where you're learning in real time while your algorithm interacts with people on a website, and which I think is great because it gives us the opportunity to just work on more of the cutting edge type of algorithms out there, and deep learning and reinforcement learning. So yeah, I mean, it's an exciting time, I think, to be a data scientist. But one thing is that, I always tell everybody, you cannot skip the fundamentals, right? You have to understand these algorithms. It's really important to have built them yourself, have a kind of an understanding of the mathematics going behind it, because that's going to make you really effective in using whatever automation tools are available, because you know what's going on, and you'll know how to tweak those things. You'll know how to prepare the data so that they work. So that's really what's going to be valuable for future data scientists, right? You got to have those basic fundamental principles down no matter what.
Yeah, it certainly is a fascinating time. All right, we are out of time. But again, I really appreciate it, David, and the people who have joined us both on Zoom and YouTube. We will send out an email with links to resources and code from the entire sequence to those who are already in our system. Feel free to reach out to us on Twitter or at Alex or David at dataquery.com. We'll be glad to answer any questions and point you in the directions for resources associated with this set of workshops. Thank you once again. We'll be in touch soon, and we're going to set something up for early 2023 on AutoML.
Yeah, thanks
all
everyone.
Right.